All right, so we have been learning about log functions. Now we're going to just take a look at what does the graph of a log function look like. So we have an example, y equals log base 2 of x. So we're going to graph this, and then we're going to identify the domain, range, x-intercept, and the asymptote, and then also talk about the end behavior of our graph. Now the issue is I can't just type in log base 2 of values in my calculator because our calculator button operates in base 10. So it's going to be more helpful to us to put this into exponent form. So to put it into exponent form, we start with our base. Our base is 2. We're going to raise it to the power of y, and it's going to equal x. So we'll set up a table of values just to kind of look at, how this is going to work out. Typically what we do is we plug in values for the x, and then that will give us the y. But it's just going to be a little bit easier if we come up with our y values first, because we can plug into this y, do 2 to that power, and that will give us the x, and then we'll just have an xy coordinate pair that we can plot. So we're just going about it a little bit backwards just because the math is easier that way. So why don't we plug in a -2, a -1, a 0, a 1, and a 2 for all of our y's. And then whatever we get back for our x's, that will be an ordered pair that we can plot on the graph. So -2, what is 2 raised to the -2 power? Well, that turns into 1 over 2 squared, which is 1/4. Now let's plug in a -1 for the y. 2 to the -1 power, we bring it to the bottom, it's 1 over 2 to the first, or 1 over 2. 2 to the 0 power, anything raised to the 0 power is 1, that's one of our exponent properties. And then the last two are pretty quick. 2 to the first power is 2, and 2 to the second power is 4. So we're going to plot these points on our graph. Just keep in mind, we're going to plot them like regular ordered pairs, the x and then the y. So if our x is a 4th, we're just going to go over a 4th, but then down 2. So this is going to be kind of close to the y-axis right there. Then we're going to go over 1/2 for your x and down 1. Then we have the point 1, 0. And then we're going to go over 2, up 1. And then we're going to go over 4, up 2. So, this probably looks similar to what we've been doing with our exponential growth and decay functions. It actually is the inverse of those. If you notice, here's 2 to the y equals x. Well, you guys did 2 to the x power equal to y. And so this is going to be the same curve, just the asymptote's going to be different. All the key features will be a little bit different, but it operates very similar. So we're going to draw this in. This is going to approach the y-intercept or the y-axis but never touch it, so that ends up being our asymptote. You can see there's the curve. It's just kind of going along the y-axis versus the x-axis. All right, so let's go through our key features. First we have the domain. So domain is our input. If you notice, our input are all of these x's over here. I can see that they are all positive. And if we look at our graph for the x's, everything is on the right side of the y-axis. These are all your positive x values. And because our graph is going to approach this line where x equals 0, it's never going to touch it. So our domain is all of the x's that are going to be greater than 0. You won't have any negative x's with these log functions. The only time you would is if your graph has a transformation. If it's shifting, then you will have some points on the left side, but then our domain shifts with it. All right, so our range, the range is the input or the y values. Our y value is our exponent this time. Can we raise 2 to any power? Can we raise it to negative exponents, to 0, to positive exponents? And we actually did that right here. There are no restrictions on your range, so it's going to be all real numbers. All right, our next key feature is the x-intercept. Now on our exponential functions, we had a y-intercept because we crossed the y-axis. But in this case, we cross the x-axis, and we got the ordered pair right in our table of values, but it's just wherever your graph crosses the x-axis. So our intercept is 1, 0. And then the asymptote is this vertical line. So asymptotes will be vertical lines with your log functions, and it's at x equals 0, which is the y-axis. Now that asymptote will shift with the graph if you have any horizontal translations, so just, be aware that that can change. But just in this function with no horizontal transformations or translations, it is just the y-axis of x equals 0. All right, and then last we have end behavior. So when we do end behavior, we think the left side of our graph and the right side of our graph. As x approaches negative infinity or as x approaches positive infinity. It doesn't matter which one you do first. Maybe we'll do the positive one. I think that's the more straightforward one with this function. So as x approaches positive infinity, that's the right side of your graph. So as our x's head this way, what's happening to the y values? Well, they're increasing. They're just going to get bigger, 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 bigger. So the y's approach positive infinity. Now, normally we would say for the left side of our graph as x approaches negative infinity. But our x's don't approach a negative infinity. We don't have any x's over here on the negative side. So what's happening is as your x get smaller, as you move to the left, they get smaller, smaller, smaller. They get closer and closer and closer to 0. You're never going to have an x equal to 0, and you're never going to have x's on the other side, any negatives. So instead of saying as x approaches negative infinity, now our x's are approaching a 0. So as x approaches 0, what's happening with our function? The y's are decreasing. They're getting more and more negative, so they approach a negative infinity. So just a little something, you got to be careful there with these log functions is your end behaviors are going to look just a little bit different about what those x's approach.